Okay, so your first quiz is due today. So if you didn't hand it in Friday, give me that before you leave class. It was originally due Friday, but everything's been pushed back a day because of the snow day. So today's gonna be our last day covering chapter 6. So this is kind of like chapters 5 and 6 are laying the sort of conceptual groundwork that we're gonna be working off of in chapter 7. So chapter 7, we're going to be learning a lot of techniques, right? A lot of sort of procedural things of how to find antiderivatives. So understanding like what an antiderivative is and how the fundamental theorem of calculus works, which we've talked a bit about, is important moving forward from here. The next thing that you have due is your project 1. Is originally due Friday of this week. You can certainly get it done still by this Friday. We've had all the material you need, but because of the snow day, it can be due at our next class if need be. Okay, quiz 1 is due today. All right, so in this section, we're going to talk about the second fundamental theorem of calculus. So there's 2 fundamental theorems, part 1 and part 2. This is part 2. Admittedly, it's kind of a funny and contrived theorem. It's interesting not for its practical application like part 1 is. Like part 1 is super useful, but for sort of the surprising connection that it illustrates. So first, a little review. We have a derivative graphed on the left. Using techniques we've learned so far, sketch an antiderivative on the right. Rough sketch, just thinking about increasing, decreasing, and concavity. And because there are an infinite number of antiderivatives, I want you to sketch the one where f of -4 equals 0. So I already broke this derivative function into 4 important intervals, because what I'm looking at in the derivative function is where is it positive, where is it negative, and where is it increasing, where is it decreasing. So I broke it into these 4 intervals because something changes on each of them. So for this first interval that I did in pink here, the derivative is positive and decreasing. All right, so when the derivative is positive, that tells me that f is increasing. It's not the same color here. F is increasing because the derivative is positive. And the derivative is decreasing, which tells me that f is concave down. So you look at the sign to tell you increasing and decreasing to tell you the concavity. So on this next interval, f prime, my derivative is negative, so that tells me that f is decreasing. And my derivative here is decreasing, which tells me that f is concave down. And this next interval, my derivative is still negative, which tells me that f is still decreasing. But now my derivative is increasing, which tells me that f switches to concave up. And on my last interval, the derivative is both positive and increasing, which tells me that f is increasing and concave up. So I try to sketch a graph that satisfies those 4 pieces, and f of -4 has to be 0. Now this is a rough sketch. We need to be sure about increasing, decreasing, and concavity, but you don't really know like how much it increases. You just know on what interval. So we don't really know y values, so we'll just kind of do our best to make a rough sketch. So increasing concave down until almost -2. So I'm going to put these little marks in here so I know 0 is an important changing point, and then a little after 2. Okay, so increasing concave down. So maybe something like that. It's increasing and concave down. All right, and then it switches to decreasing and concave down. So it's going to start coming back down, stay concave down until 0, like that. And then at 0, it switches to decreasing, but now it's concave up. So I'm going to hit a minimum at that value of 2. And then it's increasing concave up. So there's my antiderivative. Does that picture make sense to you? Should that be the shape of an antiderivative of this, something that looks like that on the left? Yeah, because this thing on the left looks like a quadratic, right? Its antiderivative should look like a cubic, right? Because the power rule would increase the power by 1. So this looks like a cubic, so we can feel pretty good that we did this right. Okay, so next, we're going to create a table of values for something brand new. We're going to call this the cumulative area function. Call it C of x. So this function is defined in sort of a peculiar way. C of -3, for example, measures the area between the curve here, the one that looks like a quadratic, and the x-axis from -4 to -3. C of -2 measures the area from -4 to -2. And we're going to assume areas below the x-axis are negative. So in other words, C of -3 is the integral from -4 to -3 of the function on the above left. And C of -2 is the integral from -4 to -2. So we're always starting at -4. That's kind of arbitrary. I just picked it. We're starting at -4. And if I ask you what's C of whatever, you take the area from -4 to the whatever I asked you for. So from C of x is going to be defined as the integral from -4 to x, whatever x I ask for. All right, so I want you to fill out this table of values. You're going to approximate the area by just drawing a trapezoid or triangles. And once your table agrees on the value of C of -4 and C of -3, you can divvy up the work in estimating the remaining areas. Put them together. Okay, so I'm doing a cumulative area function of this quadratic looking thing. So for each of these x values, I want to take the integral from -4 to that particular x value. So what's the integral from -4 to -4? 0, yeah, because there's no width under there. So that one is 0. Okay, and then for the -3, I want to take the integral from -4 to -3. So the area under the curve from -4 to -3. And I can estimate it pretty decently with a trapezoid, a rectangle, and a triangle. So this is 1 by 2, so that has an area, oops, sorry, 1 by 4. I warned you of that, and then I made the mistake. So that's 1 by 4, so it has an area of 4. And then this triangle has a base of 1 and a height of 2, 4, 6-ish. So that's 3, about. So the whole area under the curve there is 7. Not trying to be perfect, we're just getting some rough estimates to estimate these values. All right, and then this next one, this would be the integral from -4 to -2. Okay, so I already know the area from -4 to -3, so I can just add to that the area from -3 to -2. So I've got 2 triangular pieces. One's going to give me some positive area, and the other one's going to give me some negative area. Let's just say that this piece and this piece kind of cancel each other out, roughly. So then this area here, I don't know, what is that? half of 1? Sure, we'll say approximately 1. Okay, so then I just have to add 1 to the 7 that was already there, so we have 8. All right, so then integral -4 to -1. So now I just have to add the area from -2 to -1. So that's a triangle that's like 4 by 1. So it's got area approximately 2, minus that little chunk, but we'll just ignore it because it's small. So I'm going to add about 2 more here, so I get 10. What? Yes, thank you. Was the other one -2? No, okay, yeah. Okay, yeah, so that one is about 2, but it's below the x-axis, so it's -2, right? So I have to subtract that area, so I get 6. Thank you. No, that one was 8. This one's 6. Okay, so then do the integral from -4 to 0. So let's look from -1 to 0. You can estimate that pretty well with a trapezoid. So this is 4 by 1. That's got an area of 4. And then this little chunk is 1 by 1. Yeah, so a half. So 4.5. So I'm going to take 4.5 away because that's all below the x-axis. So 6 minus 4.5 is 1.5. Okay, so then 0 to 1. That's also going to be 4.5 because it's symmetric. So I'm going to take 4.5 away again. 1.5 minus 4.5 is -3. All right, and this next piece we said was about 2. Below the x-axis, so I'm going to subtract 2. So I get 1. Yep. -3 minus 2 is -5. All right, and now I'm above the x-axis again. So I have this piece, which we said was about 1. So I got to add 1 because it's above the x-axis. So I get -4. I'm going to stop writing the integrals down. And then this last one, got this trapezoid and it has area 7. So I'm going to add 7. -4 plus 7 is 3. Okay, so now I want to plot those points. All right, so I have -4, 0, -3, 7. -2, 8, -1, 6. 0, 1.5, 1, negative 3. Two, negative 5, negative 4, 3. Okay. Negative 5, negative 4, 3. Okay, so if I connect these, the nice smooth curve, what do you notice about this curve? Yeah, this looks just like the sketch that we drew in number 1 of an antiderivative that goes through negative 4, 0. Again, that sketch that we drew was a rough estimate, so your sketch might look a little bit different, but it should have the same shape. So it's got very similar look to the original antiderivative we drew. It has the exact same shape. Which kind of makes sense because we were taking integrals, and integrals are very closely related to antiderivatives. Right? All right, so now I'm going to define c of x a little bit differently. It's still a cumulative area function, but this time I'm always going to start at 1 instead of at negative 4. Find the area from 1 to x under the function. So that's the difference. The other one started at negative 4. This one starts at 1. Remember, if you want to find the integral from 1 to something before 1, you always switch it so that the smaller number's on the bottom and make it negative if you have to switch it. Okay, so fill in this table of values for this new cumulative area function and then plot your point. All right, so I took the picture from earlier with the areas filled in. It might help us fill in this table of values. So I'm looking for integrals from 1 to whatever this x value is. So the integral from 1 to 1 is sort of the easiest one. What's the integral from 1 to 1? 0. So that one gets filled in. And then it might be, it's more natural to go from left to right. So let's fill in the 2, 3, and 4 first. So what's the integral from 1 to 2? The area under this curve from 1 to 2? About negative 2. Yeah, that's this piece right here. So it's about negative 2. All right, what if I want to take the integral from 1 to 3? It's about negative 1. There's negative 2 below, 1 above, so it's about negative 1. And then the integral from 1 to 4, I got to add 7 to the negative 1, and I get 6. Good. All right, so then to go backwards, from 1 to 0, I could do 0 to 1 and just take it negative, right? So that's when you want to do an integral, say from 1 to 0. When you write integrals, we almost always put the smaller number on the bottom. And to think of it as an area function, you have to have the smaller number on the bottom. So we would rewrite this as the negative of the integral from 0 to 1. So that's a property that we talked about several classes ago. So the area from 0 to 1, this area here, is about 4.5. It's negative, right? So I'm going to make it positive because I'm going from 1 to 0. So I'm going to add 4.5 here, so I get 4.5. All right, and then from to do the integral from 1 to negative 1, that's negative the integral negative 1 to 1. So I'm going to find the area from negative 1 to 1. So I've got negative 4.5 and negative 4.5, which makes negative 9. but then I take the negative and I get positive 9. All right, so then I want to do the integral from 1 to negative 2. So that means I'm going to be adding this area right here, or subtracting because I'm going right to left. So this area is about negative 2. So I'm going to add 2 here to make 11. Did I do that right? I think I'm doing it right. Okay. And then from negative 2 to negative 3, that's like about 2. Oh, sorry, no, it's about 1. And I'm going to subtract it because it's positive, but I'm going the opposite direction. So I subtract it. And then I've got this last bit from negative 3 to negative 4, which is positive 7. But because I'm going right to left, I'm going to subtract it. So 10 minus 7 is 3. All right, so let's plot these points. Negative 4, 3. Negative 3, 10. Negative 2, 11. 4.5. Okay. What do you notice about this function? It's the same shape, but what's different about it? It's shifted. Yeah. It's shifted. Vertical shift. So it the other one went through negative 4, 0. So it got shifted up. Same function, but a vertical shift. So this function that we've been finding areas under, that it's all marked up now, is t squared minus 5. What would a formula for its general antiderivative be? Yeah, it would be a cubic, right? Because if this thing's a quadratic, its antiderivative is cubic. So I did the power rule, increase the exponent by 1, and then divide by that exponent, minus 5t plus c. And then if I want to find f of negative 4 equals 0, the particular antiderivative where f of negative 4 equals 0, I plug in a negative 4. And I have to solve for c. Plug in negative 4, you get 0, and you solve for c. Okay, so 4 cubed, I think that's 64. I think I'm going to need a calculator. So negative 4/3. So c is 4/3. Right? Okay. So that means that my function is f of t equals t cubed over 3 minus 5t plus 4/3. So that should be a formula for the antiderivative we graphed that went through negative 4, 0. And it does look like it goes through 5/3 there. Okay, so this is the same as the graph from number 3. That's the one we graphed where f of negative 4 equals 0. All right, so here's the big conclusion. This is the fundamental theorem of calculus part 2. It's a way of constructing an antiderivative, way of creating an antiderivative. If f is continuous on an interval and a is any number in that interval, right? A can be any number, then the function capital F is an antiderivative of little f, the integral from a to x of f of t dt. So it's exactly what we've been, the function that we've been creating so far. Take any constant, we used negative 4 for one, we used 1 for another. Both of them give an antiderivative, just a different antiderivative, just a different plus c. So this is a way of getting an antiderivative. Take the integral from a constant to x. So I'm going to skip the challenge for now. So the key idea of the second fundamental theorem of calculus is that you can construct an antiderivative by using an integral. Capital F of x would be the integral from a to x of f of t dt for any number a. So in other words, if you take the derivative of this integral, you'll get the function back, f of x, right? Because this guy is an antiderivative, the integral from a to x of f of t dt. If you take d dx of that, you should get the original f of x back. So t is a dummy variable, x is the actual variable in this function f of x, because that's the number that we were changing. So we were doing, for example, negative 4 to negative 3, negative 4 to negative 2, negative 4 to negative 1, negative 4 to 0. So the x is the thing that's changing. This is just a dummy variable that represents the curve f of t. We can't use x for both of them because it means two different things. So we use a t instead there. The value of a is sort of the starting point of the area accumulation function that we were doing before. So what would f of a be? Capital F of a. 0, yeah, because capital F of a is the integral from a to x, and x, we're plugging in an a now, of f of t dt, which has to be 0, because the area under a single point has no width. So there's no area. All right, so suppose I want to find an antiderivative function for radical 1 plus x squared. Do we have any derivative formulas, any functions we know that have that as its derivative? No, we have some close ones. We have like 1 over radical 1 plus x squared, but nothing exactly like this. There is no function whose derivative is exactly this. So because there isn't a formula readily available, we can construct an antiderivative using an integral. So let's all pick the same value of a. What do you want to use for a? 2? Okay. So my antiderivative of this function f would be an integral from 2 to x of this function, radical 1 plus x squared. But I already used x to mean something here, so I'm just going to switch the variable name of this function to t. So this would be radical 1 plus t squared dt. There's my antiderivative. Right, so I don't have a nice, neat, pretty formula for an antiderivative, but this is an antiderivative. It's an area accumulation function where I accumulate area from 2 to the variable to whatever I plug in for x. So I could create a table of values for this. I could plot the points. I can study this antiderivative even though I can't come up with a formula. So let's find f of 1 and f of 2. F of 1 would be the integral from 2 to 1 of radical 1 plus x squared, oops, supposed to be a t, dt, which is negative the integral 1 to 2 and because I don't have a formula for the antiderivative, I have to do this numerically. I can have my calculator do it. So I do math 9, function integral, and we put in the function square root of 1 plus x squared, comma x, comma 1, comma 2. And whatever I get, I'm going to take the negative of it, because I'm really going from 2 to 1. So 1.81. Okay, and then f of 2 would be the integral from 2 to 2 of radical 1 plus t squared dt, which would be 0. So even though I don't have a formula made up of easy functions that I know for the antiderivative of radical 1 plus x squared, I can evaluate that antiderivative at any point I want by taking an integral. All right, so if I want to find f prime of x, that would be d dx of the integral from 2 to x of radical 1 plus t squared dt. So I'm taking the derivative of an antiderivative, right? So it's going to be the function itself. And what variable am I going to use, the x or the t? X, because I'm taking d dx, right? This is a function whose variable is x, and if I take d dx, the result should have x's in it. So it is radical 1 plus x squared, the original function in x. All right, so now I'm going to do another problem like this where I take a derivative of an integral and get the function back. But I'm going to do it in 2 ways just so that to really show you the connection that it works. Okay, so first I'm going to do this way, right? The really fast, use the fundamental theorem of calculus part 2. Right? So if I take the derivative of the integral of a function, that's the derivative of the antiderivative, I should get the function back, right? I should get a cubic back. But what should the variable be? X, because I'm taking d dx. That's telling me that that's the variable, the independent variable. So this should be x cubed, right? I can write the answer down without doing any work. But now I'm going to do all the work out just to show you that that is really what you get, that the fundamental theorem of calculus part 2 is not lying. So I'm going to ignore the d dx part, and I'm just going to do this integral part. So if I take d dx, that I can use the fundamental theorem part 2 to evaluate this. That's the f of b minus f of a thing. So what's the antiderivative of t cubed? T to the 4th over 4. So I'm going to do t to the 4th over 4 evaluated from 1 to x. And I'm just carrying this d dx along. I'm going to do that last. Take the derivative last. Okay, so this is d dx of and then I'm going to do fundamental theorem of calculus, plug in the x, plug in the 1, subtract the 2. So when I plug in the x, I get x to the 4th over 4. When I plug in the 1, I get 1/4. So now I'm going to take the derivative of this thing, d dx of x to the 4th over 4 minus a 4th. So what's the derivative of x to the 4th over 4? X to the 3rd, yeah. Bring the 4 down, it's going to cancel with the 4 in the denominator, and you get x cubed. What's d dx of 1/4? 0. X cubed. X cubed. That makes sense? Okay. All right, so now we have some fun ones. This first one, d dx of the integral from x to 0. How is that written just a little bit differently than FTC part 2? Yeah, it's starting with the x. So I'm going to put the x on top just because that's what FTC2 looks like, and so then I can apply FTC2. So when you put the x on top, when you change the bounds of integration, you just put a negative in front. So I'm going to do d dx and put the negative in front of the whole thing. Okay, so what is d dx of the integral from 0 to x of b over cosine b db? So this says take the derivative of the antiderivative of this function. Yeah, negative x over cosine x. Yep. The negative from there. Right. So applying FTC2 can be pretty easy. And actually doing the work out like I did here just to justify my answer isn't always possible, right? This is only possible if you can find a nice formula for the antiderivative. And b over cosine b is a tricky one. All right, so this next one is a little bit harder. So I'm going to get a new page. Okay, so d dx of the integral from 1 to the sine of x of 1 minus t squared dt. How does that look a little bit different than fundamental theorem part 2? Instead of just an x, you have a sine of x. Yeah. So if instead I wrote this as the integral from 1 to u, and I let u be sine of x, right? And I want to take d dx of this thing. Can I apply fundamental theorem part 2 now? Yeah, I've got some like, I have 3 variables floating around now. I have x's and u's and t's. So it doesn't quite match FTC part 2. So instead of taking d dx, right, think of that as dy dx. Y will be that integral thing. I could, instead of taking dy dx, I could do dy du times du dx, and this is, what is this? Chain rule. This is the chain rule, yeah. Because this was a composition, right? I composed the integral from 1 to x with sine of x. Right? So this is a composition, so the chain makes sense that I'm going to use the chain rule to take the derivative. Okay, so dy du, that is d du of this thing. And then what's du dx? Close. Cosine x, yeah. Du dx, that's just the derivative of sine x. It's cosine x. Okay, so now I have d du of the integral from 1 to u. So this now matches perfectly fundamental theorem part 2. Usually says d dx of 1 to x, but the variable name is not important. So this is the derivative of the antiderivative of this function. So what should the answer be? One minus u squared, yeah. Because it's d du, so this is telling you that the variable name is u. So my answer should be in u's. So this is 1 minus u squared. And then u, I can substitute sine of x. This is 1 minus sine squared x times cosine x. It's tricky, right? Pulls a lot of things together. Chain rule. Derivative formulas, chain rule, and this new thing we just learned, fundamental theorem part 2. So let's just verify that the answer comes out the same if we do all the workout and not using fundamental theorem part 2. So this is integral 1 to sine of 1 minus t squared dt. Okay, so 1 minus t squared, that's an easy function. I can take an antiderivative of that, right? Which means I can use the old fundamental theorem part 1, the one that's we've been using a lot. So this would be d dx of, what's the antiderivative of 1 minus t squared? So I take an antiderivative, I'm going to evaluate it from 1 to sine of x. So that means I got to plug in a sine of x, and I got to plug in a 1 and subtract. When I plug in sine of x, I'm going to get sine of x minus sine cubed x over 3. And when I plug in a 1, I get 1 minus 1/3, which is 2/3. Okay, now I'm going to take the derivative of this thing. What's the derivative of sine x? Cosine x. And now the derivative of sine cubed x over 3. Close. Let's do it on another. So that would be d dx of, that really means 1/3 times the sine of x cubed, right? So the notation, rewriting that notation can really help remind you what you're supposed to do here. So what should I do? Yeah, it's going to be the power rule. Yes, I'm going to bring the 3 down in front. It cancels with the 1/3. So I'm going to have sine of x squared, then what? Times cosine of x, right? Chain rule. So no matter which way you do this problem, FTC1 or FTC2, you use the chain rule. So this is sine squared x times cosine x. And then the derivative of 2/3 is 0, so that part goes away. Is this the same thing that I got using FTC part 2? Cosine x minus sine squared cosine x? Yeah, I just have it written in factored form. Okay, try this one on your own.